Hello everyone, welcome to ImageGrafix Wednesday webinar. Our today's topic of discussion is on AFT Fathom software, which is typically used for incompressible fluid flow calculations. So particularly the calculations for incompressible systems are done with AFT Fathom software. I am Arjun Kapoor. I am the product manager with ImageGrafix Engineering Services. So I'll be taking you over through this webinar. So this will be our today's agenda. Particularly we would be first seeing on applied flow technology about AFT, then its industry application, then the basic formulas which are typically used in the hydraulic solution methodology. Then we would be seeing on the application typically some examples on pump sizings, pressure drops, velocity calculations, and the intelligent pump sizing in AFT using the feature IntelliQuip. In the middle of the session, if you have any questions, any doubts, you can always type in to the chat box available on the right hand side of your screen. So at any point of time, if you have any questions, please feel free to ask a question. So about AFT. AFT is Applied Flow Technology. It's an international software development and consulting company. It was founded in 1993 and has rapidly grown to be a leader in pipe flow modeling market software. Its primary focus is to develop fluid flow analysis software which is compatible with Microsoft Windows. These are the various industry applications where AFT products are widely used. We have the customers use these applications in many of the power generation systems, chemical and petrochemical systems, automotive, aerospace systems, semiconductor, pulp and paper, fire suppression, wastewater, etc. So some of the key areas where AFT products are widely used and are helping to actually develop the calculations or do the calculations in a better way. There are three products which are primarily offered by AFT. First is AFT Fathom, which is used for incompressible fluid flow calculations. Typically, the calculations for cooling water systems, firefighting systems, calculations for any of the water distribution systems, etc. are done on AFT Fathom. We do the calculations like line sizing, pump sizing, pressure drop calculations, etc. are done with it. Then particularly we have AFT Arrow. AFT Arrow, which is typically used for compressible systems, typically the steam distribution systems, tank farming systems, or any of the air distribution or compressible gas systems, etc. are calculated with AFT Arrow. We can do the compressor or blower sizing calculations, pressure drop calculations, Mach number calculations, etc. with AFT Arrow. Then the third one is AFT Impulse, which is typically for water hammer and surge analysis. When it comes to pump trips, valve closures, pump startup, shutdown situations, etc. are modeled with AFT Impulse for water hammer and surge analysis. And then we can also do the modeling with surge protection devices like surge tanks, liquid accumulators, air release valves, vacuum breaker valves, to name a few. So our today's agenda is on AFT Fathom software, which is for incompressible fluid flow analysis. So AFT Fathom is for incompressible fluid flow calculations. We can model any of the liquid systems, we can model any of the low velocity gas systems, etc. on AFT Fathom software. It uses NewtonRaphson Matrix method and the graphical user interface is quite user friendly. It has got a drag and drop interface, so you just need to bring the icon from the toolbar and drag it to the workspace. We can model any of the open, closed, branching and looping systems can be modeled with it. We can model the systems that are pressure, gravity, pump driven. It handles heat transfer, system energy balance, etc. can be modeled. We can generate various reports, graphs, layouts, etc. can be done. We can also customize the component and property database. Typically, like if you are working with any of the specific bends, tees, OLEDs, etc. All these specialty components for fittings and losses can be customized and can be added as per the needs and as per the industry standards into the database. We can it can also do the calculations for cost calculations. AFT Impulse also has the capability of handling non-Newtonian fluids using power law and Bingham plastic. So in AFT Fathom you can do for Newtonian calculations for Newtonian fluids, and you can do the non-Newtonian fluids as well. It includes the modeling of XTS, that is extended time simulation. Next is goal secant control, and the third one is settling slurries. These are the three additional modules which are additionally purchased and which work with AFT Fathom. So about the three add-on modules, like we have XTS, which is typically extended time simulation. It's the dynamic simulation of the system over time. So if you're doing any transient calculations on AFT Fathom, like AFT Fathom is a steady state package, and if you wish to do any transient calculations, it can be done with XTS module available with it. So with this, typically the system will be transient in nature. For an example, you have a pump which is working at a fixed volumetric flow rate, discharging to a tank which is of specific volume. So what is the time required for the pump to fill up the tank, or these kinds of calculations we do with XTS module. Or a better example could be an example of interacting and non-interacting tanks, where two tanks are connected with a pipeline, and typically the fluid levels are varying in both of the tanks, can be modeled with XTS. The dynamic calculations can be done. Next is GSC, that is goal secant control. Goal secant control, typically an example would be like, suppose I have a valve and which is connected into a main line across an heat exchanger. I have a junction, and suppose at the junction I want a specific temperature, that let's say I want a specific temperature of 20 degrees Celsius or 50 degrees Celsius. So what should be the opening percentage of that valve to maintain such temperature across the heat exchanger? These kinds of calculations we do with GSC. Another example could be like, I have a reservoir on the top of a hill with a reservoir discharging at the bottom of a hill. For an example, it's a gravity flow situation, and I have a valve connected in between. So typically, let's say at the bottom reservoir, I want to have a velocity of 10 meters per second. So to get this velocity of 10 meters per second, what should be the percentage opening of that valve to get the specific or the desired goal velocity? These calculations we do with GSC. So in this, our goal would be the velocity and our variable parameter would be the opening percentage. So depending on this, when it for a specific network, typically the software calculates the goal outputs. Then the third one is slurries. When it comes to waste distribution systems, waste management systems, slurry transportation systems, etc., or any of the mining systems. So typically for slurry SSL, it handles the settling slurry behavior and it simulates the pump performance. We can do the pump sizing as per the ANSI and Warman equations. Then coming over to the hydraulic solution methodology, that what it uses in the background, what formulas AFT uses in the background. So AFT Fathom uses NewtonRaphson Matrix method to solve the flow distribution in a pipe network. This is far better and much advanced than the traditional Hardy-Cross method, and it has been considered as an industry practice for last 30 years. The basic formula for Bernoulli equation, where we have the static head, we have the dynamic head and the hydrostatic head. In AFT software, it uses the term P stagnation or pressure stagnation. If let's say, for an example, the users who have seen the application, they can understand typically if AFT uses two terminologies. One is P static and second is P stagnation. So typically AFT software uses the term P stagnation that refers to total pressure, which is particularly the total of static pressure and the dynamic pressure. So the next time when you are working on AFT Fathom, and typically if you would like to view the total pressure, just view the stagnation pressure into the output report. The basic formula for pipe flow, m is equals to rho av, mass conservation equation, and typically the mass conservation is then put into Bernoulli equation, so the total formula then begins. The dynamic pressure and the static pressure can actually be combined into stagnation or the total pressure, and the solution is then represented for the total pressure in the output of Fathom. The basic formula for calculation of head loss, FLD half rho v square, the Darcy-Weisbach equation. In some of the cases it is also represented at HFS is equals to 4FLV square by 2GD. So that is also one of the formula for the friction factors constant. The friction factor is not constant, but it's a function of pipe wall characteristics and the Reynolds number, which is actually calculated by the application. It also uses the Colebrook-White equation for turbulent flow and the the traditional laminar flow equation when the flow is laminar. And you can see it also has the specific friction modules available. You can view over here the two equations typically which is used by Fathom. So let's come on to the application now. So I'll take you to the application. So particularly where you would be modeling the system we would be modeling the system on the software. So let's quickly go up over here. So I have a case typically over here. I have considered a small example just to give you an overview that what actually is going on. So over here we are determining the pump head and the power for the following system, where we are working with water at 21 degrees Celsius. We have a reservoir at 3 meters elevation, which is pumping up to a reservoir on top of a hill at 60 meters elevation. The flow requirement given is around 110 meter cubes per hour. The total pipe length provided is 300 meters, and the pipe is 4 inches in diameter and schedule 40 steel. And also they have provided like the pump is working at 80% efficiency. So let's come on to the software. So particularly when you are working on the application, so when you open the Fathom icon from the desktop, this kind of interface opens up. So over here the white color screen which you are seeing, this is called as workspace. The left hand side you have the toolbar, and the right hand side is called as the scenario manager. It comes with 5 primary windows: workspace, model data, output, graph results, and visual report. So workspace is the area where actually we draw or develop our network. The toolbar consists of all the standard symbols, like the yellow color icon if you are seeing is pump, the red one is the heat exchanger, this is for spray discharge, this is for check valve, this is for valve, area change, bend, reservoir, pipelines, etc. So as I stated, like it has got a drag and drop interface. Just select the icon and drag it to the workspace. So particularly since we have a case where a reservoir at the lower level is pumping a reservoir at a higher level with the help of pump. So this is how my model looks like. So let's connect it with the pipeline. So over here this is the pipe drawing tool where we would be developing the pipeline with. So just click on the icon and route the pipelines from the junctions. So particularly when developing the pipelines, particularly on J1 and J2 and J3, we just connect the pipelines, we just route the pipelines on just top of these junctions. For assigning the parameters, just double click on the icon. So like over here once you double click, the reservoir properties will pop out. Similarly, if you double click on pump, the pump properties will pop out. And in the third case, when you double click on the pipeline, the pipe properties needs to filled in or needs to be assigned. So for an example, like in our case when we are working, so we have a case where we are working with a specific reservoir where we have been assigned that okay, my reservoir is at 3 meters liquid surface elevation. They have also provided the pipe depth to be at 3 meters. So I have assigned these parameters. I just click OK. For assigning the discharge tank, just double click on the tank. They have provided that okay, my discharge tank or my the tank which is at the top of a hill is at 60 meters elevation. So over here we just enter the liquid surface elevation to be as 60. For assigning the pump, just double click. For assigning the pipelines, just double click on the pipeline. So once you double click on the pipeline, you can see that the pipelines given to me were of 4 inches in diameter, made up of steel, and the schedule was provided. If you remember the question, so they have provided that the total pipe length is 300 meters. So suction plus discharge is 300 meters. So over here, instead of 300, I have kept my suction pipe or P1 to be 3 meters long and the discharge pipe to be as around 297 meters long. So just to balance the total pipe length, that the total pipe length was 300, so I kept the suction pipe to be small so as to minimize any of the losses which are there on the suction site. For assigning the pump, just double click on the pump. Over here in AFT software, pump can be modeled by 5 types. Like if we have the pump curves, if we have the volumetric flow rate, if we have the mass flow rate fixed, head rise fixed, and the pressure rise fixed. These can be assigned over here. So in our case, we were provided that my pump is working at a fixed volumetric flow rate of 100 meter cubes per hour. So I just 110 meter cubes per hour. So typically I just select over here the preferred unit, that my fixed flow rate is at 110, and it has also provided that my pump is at an efficiency of around 80%. So the pump is delivering at an efficiency of 80%. If you see over here, let's go back to the software. So we assigned that my nominal efficiency of pump is 80%. And the pump is also at 0 meters, so we assign 0 as the elevation of the pump. Just click OK. For assigning the fluids, we go to analysis, we go to system properties. Over here in system properties, if you are working with a specific fluid of yours, so and you know the density, dynamic viscosity, and vapor pressure, so that can be assigned over here. In Fathom software, we have particularly made it the input parameters as to be blue in color. So you can see over here the blue tabs which are displayed are mandatory parameters and the white one is optional. Vapor pressure is optional. So for an example, if you don't enter vapor pressure over here, software won't account the cavitation calculations. So always make sure that if you want the system to check if there is any cavitation is existing, make sure you enter the vapor pressure. AFT also has provided a specific set of library. We just click over here, AFT standard. Over here there are certain fluids which are provided, so we can select from this library, although all are incompressible in nature, so that can be selected over here. We can also customize this list from here, so we can customize the list of edit fluid list. We can add a new fluid into this library. So in our case, we were working at water. If you see, we were working at water at 21 degrees Celsius. So we just go back to the application, we add water, add to model, and over here we specify the temperature that we are working with 21 degree Celsius. So just click over here, calculate properties. Once you click on calculate properties, so density, dynamic viscosity, vapor pressure automatically gets calculated. So to accept it, click OK. So once we are done with this, we can see a green color indicator on the right hand side bottom corner. So this will turn to green. Initially it is red and it will turn to green just to highlight that okay, now the model is ready to converge. So for converging, this is the radio button available on the toolbar, on the above toolbar. So that is, just click over here, run model. So once you click over here, run model, so this is how the calculations are converged on the software. So if you are working with, it will tell you that it took around 0.31 seconds to converge. The total iterations, the tolerance limits, etc. can be seen over here. To view the output, just click over here, output. So this is how the output results are displayed on the application. So if under general, you can see the number of pipes, junctions, matrix method, fluid parameters, ambient pressure, inflow, outflow, maximum pressures, etc. into the system. Under warnings, if there are any warnings being seen in the system, that can be displayed over here. Luckily my system doesn't have any warnings, so no warnings over here. Then the third tab is the pump summary. Under pump summary, you can see that our pump was working at a fixed volumetric flow rate at around 110 meter cubes per hour, where this pump is giving me a head loss of around 9.4 bar, the drop of around 9 bar. The head generated by the pump is around 93 meters. The overall power consumption is around 34 kilowatts. The net positive suction head available is around 12.74 meters from this pump. Similarly, in the pipelines, you can see the velocity, that my velocity is around 3.72 meters per second. For both the pipelines, the velocity is same because the pipe diameters are identical. So the continuity equation A1V1 is equals to A2V2 worked over here. Then you can see the drop in the pipeline, that I have a total dp stag total. If you see over here, this is the total drop that is being displayed. So in pipeline 1, the drop is around 0 bar, and in pipeline 2 the drop is around 9 bar. So that is the discharge pipe. In both the pipelines I have a head of around in pipe 2 I have a head of around 36 meters. Similarly, in all junctions, pump tab, you can see the volumetric flow rate, the mass flow rate, pressure, etc. can be seen over here. So if I go back over here, so particularly so this was the input parameters what we entered into the application. So particularly once entered, when we iterated, so this was the pipes. This is how the Fathom converges to the results. So this is what the output report is. So the power, the head, the elevation rise, etc. can be seen over here. Then in this case itself, now we have a characteristic curves which is being provided to me by my vendor. So they have provided me a characteristic equations between flow and head. So at the shutoff head value given to me is around at 0 meter cube per hour, the head is 102. At 110 it is 94 meters, and at 220 meter cubes per hour it is at 56. So let's go back into the application and let's put on these values over here. So I have already created this I have already created these values just to demonstrate you. So when I double click on the pump, so I just click over here, enter curve data. So they have provided me the volumetric flow rate and head tabs over here typically. So in this you can actually change between the volumetric and the mass flow rate, and we can change between the head and the pressure. So depending upon the input parameters from the vendor, the curves can be defined manually over here. The white color tabs which we are seeing for flow or head or pressure are mandatory. The green color tabs for NPSHR or efficiency and power are optional. We also have an efficiency data provided by the vendor, like at the shutoff head is at 0, at 110 the efficiency is around 80%, at 220 the pump efficiency is around 70%. Once we are done with this, we can then fit this curve. So we have two equations provided over here to fit the curve, that is polynomial equation and the interpolated xy data. The polynomial equation can be displayed just below to the tabs, and the interpolated equation for the change in head versus volumetric flow rate can be seen over here. So we use the polynomial equation to fit this curve. We can change the curve fit order up to 4 degrees. Once we are ready, just click on this radio button, generate curve fit. So over here you can see the curves have been represented over here. Minimum 3 data points are necessary for the software to predict the curve. So particularly the blue color one is the head rise or the pump curve, and the green color one is the efficiency curve. To select it, click OK. So it will be displayed over here as well on the main screen. Just click OK. So once we are ready, we just click over here, run model. So typically again this is how the calculations are converged. So over here now when we go back to the pump, we can see that okay, my flow requirement was around 110, so this pump is giving me a flow of around 110 meter cubes per hour. The drop is also same at around 9 bars, but the head has a bit, it has increased. So typically the new head now is around 93 meters. The power consumption is around 35. It has gone a bit up, around 1 kilowatt increase is there from the fixed volumetric flow rate. It is around 35 kilowatts. Similarly, the head loss, the loss, etc., the head, etc., for the pipelines can also be seen over here. Once we have the pump curves, we can also predict the pump curve and the system curve, that where my best efficiency point in the system is. So we can generate the graph for this. For plotting a graph, we go to the graph results. On the graph results tab, we can then plot various graphs, like we can plot for pump versus system curve, we can plot for system curve, we can plot for grade lines, we can plot for any of the specific solutions, etc. can be plotted. So right now I am interested onto the pump versus system curve. So just click over here, pump versus system, just click generate. So it will read the data points and will predict the graph. So over here now you can see the pump curve and the system curve, and eventually you can see the best efficiency point, that I am getting a best efficiency point at around 110 meter cubes per hour. We can also change the units from here, like if you would like to select to meter cubes per hour, we can specify meter cubes per hour, and this was in meters. So then we click generate. So now you can see the same curve but with the different units. So particularly I am getting a fixed volumetric, I am getting the best efficiency point at around 110. The red one is the system curve and the blue one is the pump curve. So typically like this, we can plot various graphs into the application. We can also generate various reports. So visual reports can be generated, like at a quick glance I would like to see the pressure stagnation, the pressure loss stagnation on all the pipelines. So just click over here, just click. So typically you can see the losses, etc., on both the pipelines, that P1 is around 0 bar and P2 is around 9.4 bars. So over here in particularly onto the if we go back onto the presentation, so this is what we did. So we entered the flow, the volumetric flow rate, head parameters, then we entered we just generated the curve. We saw the curve, how it is generated on the application, and these are the calculated results with the new pump curves what is being provided. And we also saw the pump versus system curve, which is then generated by the application, and then I can see where my best efficiency point is at. So if we see the graph of the system curve and the pump curve, the blue color one was the pump curve and the red color one was the system curve. So where the system curve is meeting and where the system curve is starting to meet the best efficiency point or to intersect the pump curve, that is the friction. The below one is the static head. So on a total we call it as HS and HF. So we call it as total dynamic head or TDH. So the operating flow rate was around 110.7 meter cubes per hour. The total dynamic head is around 93 meters. The static head is around 57 meters and the friction head, which is calculated, is around 36.9 meters. So let's go back to the software. Suppose for an example, I go back to the previous case that my pump is working at a fixed volumetric flow rate of 110 meter cubes per hour. So in the same case, suppose I don't have the pump characteristic curves available with me. So over here in AFT software, we have an option available which is called as IntelliQuip, typically where we can go to the pump vendor's website and pick up the pump curves, request for quotations, etc. So just click OK and we run the case again. So once the calculations are converged, so please remember that this case was with fixed volumetric flow rate of 110 meter cubes per hour. So for going to the pump vendor's website, we have an option available on the output report itself by the name suggest pump. We click on this icon, a small pump icon with a small gray color pump icon is actually available. So just click over here, suggest pump. Once you click over here, you can see the operating head, the flow rate, NPSHA, which is calculated by the software. Our criteria provided was a fixed volumetric flow rate at around 110 meter cubes per hour. Once done, we now go to the source database and we click internet and we select internet. Over here you can see IntelliQuip specified. So once it is done, we click over here search. So these are the various vendors which are currently available in the IntelliQuip hostname. They can be added over here. We can add a new pump vendor into the IntelliQuip hostname, so we can add them. So typically these are the various vendors, like you have Barclay Pumps, Blackmore Public, Clyde Union, Pumpworks 610, Roofram Pumps, Paco Pumps, etc. So suppose I'm going with Clyde Union. I don't know, I like them, so I'm going with Clyde Union. Just click over here, open web browser. So once you click on open web browser, it will automatically take you to the pump vendor's host name or IntelliQuip ID. This requires an internet connection. So since it was in the database, so this requires an internet connection. We just click over here. So this is how it comes up to be. So I have a flow requirement for what around 484 US GPMs. You can change it to meter cubes per hour depending on your requirement. Like I want at around 110 and my head requirement was around 65 meters. So I just specify over here with my units. Once done, just click over here next. A small radio button is there for next. Once you click on next, so these are the various pump vendors which are currently offering the pump which meets my criteria, the various types of pumps. So depending on the maximum flow, maximum head, suction pressure, etc., you can select to the specific type. Like I am selecting the fourth one over here by the name BB2 CUP. So I specify it comes with a maximum flow rate of 3000 meter cubes per hour, and it comes with a maximum head of around 300 meters. So just check in over here, just check this small select option over here, then click next. So once you click next, so you will be displayed to the various curves which are available at various speeds. So for an example, this is the pump which is meeting my requirement. It is working at 68% 3 efficiency. Its power is around 38 horsepower. The NPSHR is around 3.7. Maximum power it could go around 50 horsepower. So I just click over here. So once you click over here, the graph would be displayed to you. So particularly you can see the curves, the various power data, you can see the efficiency, NPSHR, you can see the pump curves, etc. So okay, this pump is meeting my requirements. So now we click over here, download. So once you click on download, it will ask you to save the downloaded file. So the downloaded file is in IQX extension. So you need to save that file to your desktop or whichever location you are working on. It can be saved. So it has been downloaded in my background. So let's go back to the application now, and we click over here. On the same interface, we click over here, step 2, open previously downloaded file, and we click over here, open file. So once done, we now need to root the file at where it is downloaded. So normally on my PC it goes to the downloads folder. So I just click over here, go to the downloads folder. So this is the file which is being downloaded right now. So CUP BB2 is the file. This file is available at an extension of .iqx, which is called as IntelliCube transfer file. So just select it, click open. Once you click open, so now you can see the pump curves which are displayed, so which is being imported right now. So I would like to apply this, so just click over here, apply pump data. So once you click over here, apply pump data, so I would like to apply it on pump number 2. Just click over here, change junctions, and select the pump which you wish to apply the data to. So just click over here, then click. You can even add it to the database if you want to keep this pump into your database, that next time when you are modeling a same system or the pump with the same requirement, so it can be selected depending on the requirement. So just click OK. So then it will highlight you the selected junctions on the workspace will change to the suggested pump. Do you want to continue? Yes, I want to continue. So the workspace changes are now completed. So once we are done, we can close this window. We can go back to the workspace. We can go to the pump, just double click, and now we can see the pump curves are automatically imported in that case. So you can see all the pump curves which we picked up from the vendor's website are now imported into the system. So this is a very intelligent feature of the software where it helps users to actually intelligently size the pump and pick up the pump characteristic equations. So just click OK. This pump is working at 1765 RPM and the impeller is around 22.64 inches in diameter. So just click OK. We will now run the case. Again, run the model, view output. Under pump summary, you can see the flow rate has increased a bit. Now my pump is giving me a flow rate of around 200 meter cubes per hour, and the drop is around 17 bar. The power consumption has quite gone up very high, and the NPSHA can be seen. We can also plot this diagram in this form, so where particularly you can see the pressure You can see the NPSHA, overall speed, power, efficiency, etc. This can be copied and can be pasted on the reports, etc. So typically on the graph results now I can plot the pump versus system curve graph and can see where the best efficiency point of my system is at. So particularly in this way, users can actually particularly import the datas and can intelligently size the pump curve into the software. So with this particularly we come to an end of this webinar. So if you have any questions, please feel free to type into the chat box. So any of the questions, if there are any questions, please type into the chat box. You can also email me the questions at a later stage as well. My email address is now displayed onto the screen. So particularly you can email me all your queries. So we have a question over here, like on the chat box of mine, like how to see the Reynolds number. Okay, so let's go back to the software now. So once we go back to the software and we have converged our solutions, and on the output report, and particularly you don't have Reynolds number, so Reynolds number would be displayed on pipelines. So I would zoom in a bit over here. So Reynolds number is not displayed right now. So no problems, we can add the Reynolds number onto this output. So for this we have an option by the name output control. So this output control is actually the engine which controls everything into the system. So typically we go to the output control and we go over here on the output control tab, like the pipes, we can add the various parameters for pipes, for junctions, for pumps, valves, heat exchangers, reservoirs, etc. So on the pipelines, when I go, I select for Reynolds number, I search Reynolds number. So I need to drag down, or you can press the R key for Reynolds number. Oh, here it is. So Reynolds number, then click add. So once you click add, it moves on from the left hand side to the right hand side. So the right hand side parameters are currently displayed on the report right now. So we go to add, Reynolds number is now added, then we click OK. So once we click OK, so you can see the Reynolds number now added up over here. So it's a turbulent case, so you can see the Reynolds number. So this is the way by which you add the Reynolds number onto the output report. Alright, so we have few more questions over here. So there are 4 questions right now, so I'll go one by one. The first question is, can we model spray sprinkler system along with the pump system fire water network? So yes, the answer is yes. We can model the spray system along with the pump, typically pump system on the fire water network. I can show you an example as well for this. So particularly when we are modeling a fire sprinkler system or fire fighting systems, spray discharge systems, etc. So there are two options in AFT software where it can be modeled in the where the fire sprinklers can be modeled into the software. So we have an icon of fire sprinkler on the toolbar. So if you see the icon just up next on the right hand side of the pump, or you can say on the right hand side of the reservoir, is the icon for spray discharge. So just drag and drop the icon. So a very specific system just to represent how the firefighting system works in AFT software. So when we double click on the spray discharge, there are 3 options in which we can model the sprinkler or a fire nozzle in AFT software. The first option is CD, that is coefficient of discharge. If we have a specific coefficient of discharge available with me and with a specific discharge flow area, so this would depend on the geometry of the sprinkler. So this can be specified over here, that the specific discharge coefficient and the discharge flow area. Then we can also use it as a K fire sprinkler, where K, the basic formula K is equals to Q upon under root of delta P. So that can be displayed over here. So we can select it as a K fire sprinkler, where I would be providing the Q per square root of the exit pressure, that is the per square root of the pressure drop. And second, the last one is the resistance curve. Over here in resistance curve, if you have a specific if you have a pressure drop available with you, that let's say for an example at 10 GPM I have a pressure drop of around 0.9 bar for an example. So just specify the unit bar over here. So this is the way where how it is used in AFT software to particularly assign the pressure drop. So in my case, I have at 10 GPMs I have a drop of around 0.9 bar. Then just enter these datas, then click over here, fill as quadratic. So automatically the volumetric flow rate and the pressure equations would be fitted as quadratic. Then click over here, generate curve fit. You can see how the curve is coming now for the pressure drop assigned by me. Once done, just click OK, and then particularly you can view the results. If I converge this case, so in this case you can actually now see then the pressure drop for all the pipelines. We can see the volumetric flow rate, we can see the drop, we can see the sprinklers, we can see the net volumetric flow rate from the sprinkler, pressure from the sprinkler, etc. can be displayed. So this is the way typically how it is used for putting the or for calculating the or modeling the sprinklers over here. So I hope I have answered the query. So our next question is how to add new pump vendor. Okay, so let's go back and open the case what I was displaying over at the beginning of the session. So I open that case. So let's say for an example I am working with a fixed volumetric flow rate situation, that my pump is working at a specific volumetric flow rate. So we run the case, we go to output. For adding the vendors we need to go back onto that option for suggest pump. So once we click on suggest pump, we then see the pump, and then we can go to the internet, we can specify the source database as to be internet, then click search. For adding the vendor onto this IntelliQuip host name, just click on this radio button add. So this requires a login description, maybe the vendor's name, that can be provided over here, and they would be providing as an IntelliQuip login ID and password for this specific host name, ieq.intelliquip.com. So particularly this would be the area where we would be adding those vendors onto the IntelliQuip hostname list currently available on the software. So if you need any further information, I would request to email me and I could answer it on a more specific way. So let's go on to the new question now. So we have a question that limitation on viscosity or other limitation of software. Uh, I'm sorry, like I'm not able to get up the question. So maybe I would request to kindly email me all your query. Typically limitation on viscosity. As such, there is no limitation on viscosity into the software, but if it's a viscous fluid, yes, we can change the viscosity, we can apply the correction parameters on the pump as well, that can be done. So if there is anything, I would request to kindly email me. Then there is another question, what is the difference between a T and junction and what is the criteria of use? Okay, so T and a junction. So this is the T and this is the junction. We call it as branch as well. The difference between T and a junction is this junction can actually connect up to 25 pipelines. So in this 25 pipelines, it can be 24 inputs and 25 outputs can be there. So typically, depending on my requirement, this junction will work. The major difference between junction and T is like from I have a main header line. From the header line, I have 4 tappings coming out. From the main, let's say I have a header line of around 16 inches. From the 16 inches header line, I have 4 tappings coming out of around 2 inches each in diameter. So this can be represented with a branch. So with the branch, when you go over here, you can even give the loss value, the K value for the inflow and outflow for that branch on the specific pipelines. That pipe 3, pipe 4, pipe 5, pipe 6 over here in this case has specific K values. And in T can only connect up to 3 pipelines, not more than that. So the major differences between T and branch is branch can also be frictionless and can handle up to more than around 25 pipelines, whereas T only handles at around 3 pipelines. So I hope I have answered your query. So then we have another question, that what is the implication of negative value in head rise and the output while doing the pump sizing? In this case, typically the negative value replicates a situation that there is a backflow into the system, that the pump is working in a reverse direction. So I don't know that where you are getting this value or how it is being generated. I need to see the system. So I would suggest to kindly email me the specific model and the query for a detailed answer on this. Then there is another question, temperature rise of fluid in case of closure of valve outlet, pump discharge. Okay, yes, this can be handled. For this, we need to model the heat transfer case. So particularly with this, as such, if there is any mechanical energy what is converted into heat and that is being transferred to the liquid, up to some extent, yes, we can model it. But although to model these cases, we need to develop a heat transfer model. So this can be seen under examples. There are various files available which handles the heat transfer cases for the pumps. Then we have VFD drive system modeling. Yes, VFD drive system modeling is possible on the application. So to model it, we go to pump curve, we go to enter curve data, and then we click over here multiple. Right now what we see is the simple configuration. Then we can go to the multiple configuration over here. Under multiple configuration, I can create the various RPMs, VFDs, etc. Like the VFDs are installed, so RPM would change accordingly. That can be provided, and the new curves can be assigned and can be used to converge to various results. If there is another question, if I have an exchanger, how do I account to change in density across exchanger? AFT software is an incompressible package, so we don't account for the density changes, or we can say the major density changes. If there is any change in temperature, that can be accounted from the heat transfer option. Can we model pressure vessels in the system which contains liquid as well as gas? Yes, we can model the pressure vessels which contains liquids as gas. For this, impulse would be the product which can handle this case. How to add a fixed pressure drop? Okay, so for adding a fixed pressure drop into the case, we can model the system as a resistance curve, or if there is any specific component which is creating or which you would like to model as a fixed pressure drop, so that can be done over here. We have an option of general component. The last option, general component. This general component can be used in all those areas where you don't have a specific component available in the toolbar, and that is creating a pressure drop into the system. So for assigning a fixed pressure drop, you can give the K value. So this is a loss value. This is not the pressure drop. This is the loss value. You can give the K factor, or then you can give the resistance curve for the volumetric flow rate or head or pressure equations. So with this will act as a particular pressure drop into the case, which will work as a fixed pressure drop situation. So I would suggest to use a general component at that location. So with this, I hope I have answered all the queries. If any of the queries is still missing, or any information you may need more, I would request to kindly email me with the query. So in a small session, although you can understand it's very difficult to take up all the queries, but although I have tried my level best to answer all the queries, so you can email me the queries any point. So with this, we come to an end of the webinar. So I hope you have found the webinar useful and would have been working with AFT software, or would have been trying to use or implement AFT software with this onto your systems. So thank you everyone. Thank you for your valuable time, and I hope the webinar must have been useful, and stay tuned for new webinars on the same. So thank you everyone.